Lesson: Semi-supervised learning, bridging supervised and unsupervised approaches. Semi-supervised learning represents a pivotal paradigm in the realm of machine learning, standing as a bridge between supervised and unsupervised learning approaches. Its significance lies in its ability to leverage both labeled and unlabeled data, a necessity in real-world applications where acquiring labeled data is often costly and time-consuming. The vast availability of unlabeled data, paired with the scarcity and expense of labeled data, underscores the importance of SSL in practical scenarios. Central to SSL is the assumption that the data lies on a low-dimensional manifold within a high-dimensional space, which enables the transfer of information from labeled to unlabeled data. This manifold assumption facilitates the learning process, allowing models to make more accurate predictions even when limited labeled data is available. The practical application of SSL can be illustrated in several domains, such as natural language processing, image classification, and bioinformatics, where labeled data is often scarce. To implement SSL effectively, several strategies can be employed, including self-training, co-training, and graph-based methods. Self-training involves a model being initially trained on a small labeled dataset, which then iteratively labels the most confident predictions from the unlabeled data to expand the labeled dataset. Co-training, on the other hand, involves two models being trained on different views of the same data, each model labeling data for the other, thereby enhancing their generalization capabilities. Graph-based methods construct a graph where nodes represent data points and edges represent similarities between them, allowing for label propagation throughout the graph. Frameworks such as scikit-learn and TensorFlow offer tools for implementing SSL methods. Scikit-learn, for example, provides semi-supervised classifiers like label propagation and label spreading, which can be efficiently utilized with minimal labeled data. These classifiers propagate labels through the dataset based on the similarity between data points, capturing the underlying structure of the data. TensorFlow, with its flexible architecture, allows for custom implementations of SSL techniques, providing the necessary tools to build and train models with both labeled and unlabeled data. A practical example of SSL in action is its application in the field of medical imaging. Annotating medical images requires expert knowledge, making labeled datasets expensive and limited. SSL techniques can be employed to train models that identify tumors or other anomalies with high accuracy using a small set of labeled images alongside a larger set of unlabeled ones. By leveraging the manifold assumption, these models can effectively learn from the abundant unlabeled data, reducing the need for extensive labeled datasets and accelerating the deployment of AI solutions in healthcare. SSL also finds applications in customer sentiment analysis, where labeled data is again limited. By utilizing SSL, businesses can train models to understand and predict customer sentiments from a vast pool of unlabeled reviews or social media posts. This allows companies to gain insights into customer preferences and feedback without the exhaustive task of manually labeling large datasets, thereby optimizing their marketing strategies and enhancing customer satisfaction. The effectiveness of SSL is further exemplified in a study by Zhu and Goldberg, which demonstrated that SSL could achieve comparable performance to fully supervised learning while using significantly fewer labeled instances. This efficiency is crucial in scenarios where rapid deployment and adaptation are necessary, such as in disaster response systems or dynamic market environments. Despite its advantages, SSL is not without challenges. The quality of the unlabeled data and the degree of noise can significantly affect the model's performance. Consequently, it's crucial to pre-process and clean the data meticulously before applying SSL techniques. Additionally, the choice of algorithm and parameters in SSL requires careful consideration and tuning, often necessitating domain-specific knowledge and experimentation. Continued advancements in SSL are essential to address these challenges and expand its applicability. Research is ongoing to develop more robust methods that can handle diverse data types and distributions, ensuring that SSL remains a vital tool in the machine learning toolkit. The integration of SSL with other learning paradigms, such as transfer learning and active learning, also holds promise for enhancing its capabilities and expanding its use cases. In conclusion, semi-supervised learning offers a compelling solution to the challenges posed by limited labeled data, enabling more efficient and cost-effective model training. Its application across various domains highlights its versatility and potential in addressing real-world challenges. By understanding and implementing SSL techniques using practical tools and frameworks, professionals can unlock new opportunities and drive innovation in their respective fields. As the field of machine learning continues to evolve, SSL will undoubtedly remain a key player in bridging the gap between supervised and unsupervised approaches, facilitating the development of more intelligent and adaptive AI systems.